Diffusion with low-rank adaptation techniques. This we will hear from Alexander Kovalchuk, a deep learning engineer at Prequel Incorporated. Alexander will speak on advanced fine-tuning techniques for stable diffusion models, such as hypernetworks and low-rank adaptation methods, discussing the pros and cons and applicability beyond image generation. We will gain insight in how these approaches can enhance a variety of downstream tasks. Alexander, welcome to the stage.
Nice to meet you. Hello, everyone, and thank you all for coming today. I'm happy to be here, and I'm very excited to present you my talk, Fine-Tuning Stable Diffusion with Low-Rank Adaptation Techniques. My talk will be a bit technical, but I will dive into some technical details, but I'll try to do my best to do it in simple words so everyone could understand what is happening under the hood. So, just a minute to promote myself. My name is Alexander Kovalchuk, and I'm a machine learning engineer. I would say that I have a pretty diverse background in different areas of machine learning, classical machine learning, predictive analytics, text analysis, big data analysis, computer vision, and also deep learning. For the past 3 years, I've been working at Prequel, and my primary focus right now is generative AI in the computer vision area. During this time, I gained some unique and valuable experience in building and training custom generative adversarial networks, optimizing them both for server-side and mobile real-time on-device inference, utilizing GANs for synthetic data construction, and also building custom solutions based on the recent denoising diffusion probabilistic models. Just a few words about Prequel. I would say that we are a company which makes one of the best photo and video editing apps on the market. Our company inhales its unique aesthetic vision into users' content, and that helps reveal their creativity. Also, we have solutions that cover different users' needs. It's Prequel, Geo, OG, and ST. And if you haven't tried them out yet, you should definitely do it. And I'll leave some download links after my presentation in the Q&A session. So feel free to download them, and I'm sure that everyone will find some unique style and to match your photos and videos. So let's begin with a simple question. What is a generative model? Probably if you are sitting in this hall, you are already familiar with it, so I'll be concise. A generative model is a type of model which is able to produce some output signal that has similar characteristics or similar distribution with the data it was trained on. In terms of signal, it can be anything. It can be texts, audios, videos, images, etc. And often these models are built in a way that allows to incorporate some sort of conditional information into the generation process. So that's why they are often referred as conditional generative models. So in this talk, we'll be primarily focusing on image generation models with text description as a condition. So what is a denoising diffusion probabilistic model? It's a type of model that greatly boosted this area in the latest 1.5 years. It's built on a simple and beautiful mathematical concept. So it consists of 2 stages. The first one is the fixed forward diffusion process, and the second one is called generative denoising diffusion process. So the first process consists of multiple steps, and at each step we add some random Gaussian noise to our input signal, in this case to the input image, and that results in a gradual signal degradation till we get the pure noise. The second part is the part where the magic happens, and it's often parameterized by some neural network. It's a generative reverse denoising process. So this network iteratively removes the noise from the input signal until all noise is removed. So it acts as some kind of hidden Markov chain, parameterized Markov chain. And the way that we add and remove noise from the signals matters a lot, and it's called the noise schedule. But unfortunately, we don't have a lot of time to speak about details of this process during my presentation. So feel free to find me during coffee break so we can discuss everything that wasn't covered during my talk in detail. So let's dive into the famous stable diffusion model. It's a text-conditioned image generation model, which was produced by Runway ML and Stability AI, also known as the ComFIS group. And it belongs to the class of so-called latent diffusion models. It includes some pre-trained models like variational autoencoder, which is able to significantly compress input image to some entity called latent. So you can just refer to it as a minimized version of an image. So instead of operating in an image pixel space, this model operates in an image latent space. Also, it includes some other pre-trained models like OpenAI Clip in order to perform text description encoding. And the most important part is obviously the denoising unit. So it consists of several downsample blocks followed by the mid block and several upsample blocks. And each block is a mixture of ResNet and cross-attention blocks. So this model accepts some noisy latent as its input, as well as some text embedding from the text encoder and time-step embedding, and it predicts the noise that it sees in the image. And then we use some noise scaling strategies in order to remove this part of noise from the noisy latent, and then this process repeats several times. So this architecture is very powerful because it is able not only to solve plain text-to-image generation, but also various tasks like image-to-image translation, image and painting, and also it was applied to audio generation models, so you can use it to generate some music, for example. So what does it mean to fine-tune such type of a model? Usually it means that we want to refine existing generations in order to boost quality, or we want to incorporate some new style or object into the generation process that the model hasn't seen during training. So in order to do it, there exist several methods like textual inversion, hypernetworks, full or partial fine-tuning that we'll cover on the next slides. But sometimes we may even want to incorporate some new sort of conditional information into the generation process. And in order to do it, there exist several methods like control nets and AP adapters, which are able to fine-tune this type of model without tuning the whole model itself. So during my talk, I'll only cover the first two options. So we'll talk about incorporating style and object into the generation process. So let's begin with a textual inversion approach. So since we work with a text-conditioned image generation model, we may come up with a simple assumption that having some precise description for our concept, for our style or object, it could help us during the generation process. And in order to do it, we introduce some new embeddings into the text encoder model, and we only fine-tune them, so the other parts of the model remain fixed. And you can refer to this process as finding the best single or multiple words that describe your concept, your style or object. And the training process works as follows. So you modify your tokenizer, you add some new token to it. In this example, it's S asterisk. And you associate several embeddings in the text encoder model with it, and you initialize it with some initial value, some phrase that is close to the concept you are trying to fine-tune. Then you take a bunch of images alongside with text descriptions that contain this new token, and you preprocess your images with variational autoencoder in order to get latents. And you pass your text description to text encoder in order to get text embeddings. Then you add noise to the latents to get the noisy latents. And then you pass this text description and your noisy latents into the UNet model. It predicts some noise. And then you compare it with the noise you've originally added to the image. And you use some sort of mean-squared error loss and backpropagate the gradients to your newly added embeddings. So you are like fine-tuning these words. So the fine-tuning process looks pretty straightforward. And here are the results of fine-tuning textual inversion or textual embeddings on my own personal photos. In terms of pros and cons, this approach is very lightweight. So the output textual embeddings, they weight up to several hundreds of kilobytes. and it's pretty easy to fine-tune. And also, it's like a plug-and-play solution. So if you fine-tune your textual embeddings on one checkpoint, you can reuse it on different Stable Diffusion checkpoint, which has the same clip text encoder. So it's also transferable. You can, I don't know, take anime style trained model and generate yourself in anime style. But as you might guess, this process, it's hard to get results that are similar to the full fine-tuning. So if the model hasn't seen something like what you are trying to train during the initial training, it's hard to come up with this concept. So it's more of a refinement method than the full fine-tuning. Regarding the Hypernetwork approach, there was a paper posted by Google. It was called Hypernetworks, but the Google's main idea was to construct some neural network which predicts the weights for another network. But when we are talking about hypernetworks in terms of stable diffusion, the approach is a bit different. So it was presented by Novel AI in one of their blog posts. And the main idea is to modify the cross-attention mechanisms. Before doing cross-attention, we add some multi-layer perceptrons, some just linear layers with intermediate activations to modify keys and values before calculating the cross-attention. So the training process remains the same as in textual inversion. So here are the results of Hypernetwork fine-tuned on my own personal photos. So in terms of pros and cons, it's more like a full fine-tuning method. So it's similar, but in reality, it has some poor convergence. And as a downside, it only modifies cross-attention layers. But as I've already mentioned, this model has some convolutional parts as well as attention parts. So we doesn't touch convolutional part in this approach. And also, it's checkpoint dependent. So you cannot fine-tune Hypernetwork on one base checkpoint and then transfer it to another. Because the distribution of keys and values may vary between different checkpoints. So regarding the full or partial fine-tuning, everything may seem straightforward. You just have a bunch of photos and a bunch of text descriptions. You pass your photos to the VAE part and text descriptions to the clip text encoder, and then you use this information to train the model. But in reality, diffusion models are prone to so-called catastrophic forgetting. So it's a situation when the model is able to produce images similar to what we're trying to fine-tune, but it forgets everything it has seen before during the initial training. So Google came out with a simple and effective idea to cope with this problem. It's called DreamBooth, and it's just a mixture of fine-tuning textual inversion alongside with fine-tuning the base model. So they also add some regularization images into training, and that helps a lot to cope with the problem of catastrophic forgetting. And here are the results of fine-tuning DreamBooth on my own personal photos, and as you can see, it's superior to other methods. And in terms of pros and cons, yeah, it produces the best results, but it comes with a price. So it's pretty heavy approach because you need to fine-tune the whole model. And if we are talking about stable diffusion, it's something around several gigabytes. And if you do it for lots of users, you need to store this model somewhere. So also it has a downside because the output model, you cannot transfer this trained concept to another base model. If you would like to experiment with other models, like anime-style models or some other models, you need to retrain from scratch. So it's also one of the downsides. So let's spend some time analyzing how much memory is required in order to fine-tune such type of a model. So Stable Diffusion is a relatively small model by 2023 standards. It's a bit more than 1 billion of parameters. And the most heaviest part is, of course, the denoising unit. It has something around 860 millions. And it's also worth mentioning that often during fine-tuning, we fine-tune only the UNet part and text encoder part, and the other parts remain fixed. So, but as you can see, the VAE part is the lightest of this model ensemble. So imagine that we are trying to fine-tune this type of model on a consumer GPU with 16 gigabytes of VRAM, and each gigabyte is represented by a square here. A bit of a disclaimer, my calculations may not be very precise. It doesn't take into account different torch memory allocation, some intermediate activations, etc., but the main idea should be fine. So the variation autoencoder in FP32 takes something around 700 megabytes. The clip text encoder takes additional 800 megabytes. The heaviest part, UNet, takes something around 3.5 gigabytes. So in order to perform optimization, you need to store your gradients, and you need to store one gradient for each of the optimized parameter. And in this case, it's something around 4.5 gigabytes if we fine-tune both the clip text encoder and UNet. And last but not least are optimizer states. So if you are using some optimizers like Atom, which are the most common nowadays, and the most popular one, you should be familiar that it has large memory requirements. It's roughly 2 times the number of trainable parameters. So in this case, it's 9 gigabytes. And we came to the situation when we are not able to store everything on our GPU. So the first and the most obvious thing to do is to reload our models in FP16 and fine-tune it in the mixed precision. So we almost decreased the memory required for our models and gradients by half. But I'm pretty sure that you still need to store your optimized states in FP32 in order to perform optimization. And we can see that we have some free memory on our GPU, so we will be able to fine-tune something, but as I've already mentioned, my calculations doesn't take into account intermediate activations and all this stuff happening behind you in Torch. So are there any other methods that would allow us to fine-tune such a type of a model and also do it reliably, so in order to get the best results? And of course, the answer is yes. Today, there exists various of different parameter-efficient fine-tuning techniques. And one of them is the LoRA, and it's probably the most popular one and the most adapted by the Stable Diffusion community. So we'll focus on it. So what is LoRA? LoRA stands for the low-rank adaptation, and its beauty lies in its simplicity. So imagine that you have some linear layer which transforms D input features into D output features. So it can be represented by an equation H is equal to W0 times X, and W is, in this case, a matrix D by D. So when we use LoRA, we introduce some new matrix delta W, which is like an addition to the base weights. And it's also of size D by D, but we represent it as the dot product of 2 base matrices, B and A, B of size B by R, and A of size R by D, sorry. And we only fine-tune these matrices. And R, in this case, is the LoRA rank, and the more R is, the bigger LoRA gets, so we get bigger matrices, and probably better results. Also this approach is very cool because you can use the same base checkpoint and fine-tune different LoRAs for different downstream tasks. So it's like training an adapter for your model. Also, LoRA significantly reduces the number of trainable parameters, and you get and there are also some empirical studies that showcase that you get similar results to the full fine-tuning. Also, we can merge these LoRA weights into the base model, and we can get, it won't influence inference latency at all. And we can also extract LoRA from the 2 base checkpoints, so we can calculate pairwise difference between the corresponding layers, and then use some sort of decomposition, like singular variable decomposition, in order to get this BNA matrix. And also, this approach, it could be applied to different sorts of layers, not limited to linear. It can be applied to embedding layers, convolutional layers, and all other sorts of layers. So when we talk about the performance of image generation models, it's pretty hard to measure it. So I'll refer to the large language models, and we can take a look at the open LLM leaderboard made by Hugging Face. And if we look at the top models here, you can see that a lot of them are some fine-tuned versions of some base models, and they are often fine-tuned with some mechanisms like LoRA or QLoRA. So in my opinion, it showcases that these methods are able to produce meaningful results, results that are comparable to the full fine-tuning. Also, in terms of memory footprint, LoRA heavily reduces number of trainable parameters, so we spend less memory for our trainable parameters, less memory for storing our gradients, less memory for storing optimizer states, and more memory to increase our effective batch size. So in this toy example, we have almost more than 6 gigabytes free out of our 16 gigabytes card. So it's also pretty cool because I used a very large LoRA rank here, 128. So another problem that we had is that the output checkpoint size in DreamBooth training is very big. It's several gigabytes. And if we use LoRA, we can just store it alongside the base checkpoint. And of course, the output LoRA size depends on the rank, but we can get output models from like tens of megabytes to several hundreds of megabytes. And it's also pretty cool because you can use it in different downstream tasks and just store these base LoRAs. Also, the community got very creative with training various sorts of LoRAs. There is a famous portal called cvti.com, and you can find here a lot of different adapters for different character style LoRAs, anima style LoRAs, pixel art LoRAs, and also LoRAs for generating long cats. So another cool stuff that we get when we talk about LoRAs with Stable Diffusion is that we now have an ability to mix different LoRA styles together. So it allows us to get some unique styles that haven't existed before. So in this example, I used some detailed tweaker LoRA with Van Gogh LoRA, and I got some results that would be hard to get with other methods. So you can be creative and mix all sorts of concepts that haven't existed before. Also, I would like to mention that the community got very creative with different sorts of adapters for this type of models, and I would like to mention the famous Lucoris paper. It contains some different implementations of matrix factorizations behind this LoRA approach. So it's LoHa and LOCR. LoHa stands for low-rank Adamant product, and it uses Adamant product instead of the dot product, and it's also represented by 4 matrices or 3 matrices and sometimes, and it should be superior to LoRA because theoretically the output rank of the LoHa should be larger than the one in LoRA, and you should be able to get better results with smaller checkpoint size. And when we talk about LoCR, LoCR stands for Kronecker product, and it uses Kronecker product instead of the dot product, and it's multiplicative power. So when you use LoCR, the output rank is a multiplication of the ranks of these 3 or 4 matrices, and you should get even smaller checkpoint size with comparable performance. And there are some empirical studies that showcases that using Lucoris adapters, when using Lucoris adapters, you are able to get even better results, the better details. And in this example, you can see that the Lucoris adapter contains more fine details of this image, and they were trained on the same set of data with the same techniques, just the adapter was switched from the LoRA to another one. So last but not least question that needs to be answered. So how can you use it in your day-to-day tasks? And in order to do it, I would recommend using a Hugging Face PEFT library. it contains implementation of different sorts of adapters. And it also has pretty good documentation. There are some examples on how you can use these methods in your image description tasks, image generation tasks, large language models, audio generation, so all sorts of tasks. And I'm also very proud that I participated in this project as an individual contributor. So it was a great experience, and I would like to thank Hugging Face for this opportunity. So thank you very much for your attention, and let's connect on LinkedIn.
Okay. Alexander, let's see if there are any questions on this. Yes, here.
Hi, thanks for the great talk. I just want to ask, are there any limitations to fine-tune using LoRA different text-to-image models like DALL-E or something like it?
So yeah, thank you for this question. And in terms of the DALL-E models, they are mostly closed source, so we don't know how they work under the hood. They're just assumptions, but I suppose that they also use some sort of techniques for fine-tuning for different tasks as well. Yeah.
Yeah.
We have three, sorry, yeah, sorry.
Yeah, so you mentioned this chronicle forgetting of the models.
Catastrophic forgetting. Yeah.
Yes,
Okay.
and then later on, you mentioned that in order to fit your model into the limited VRAM of the GPU, you had to do things like reduce the precision to half, reduce I'm assuming the parameter count of the model as well. So do you think there is a correlation between making your model very small, very fast, and this chronicle forgetting when you're considering that you want really precise results? So
yeah, thank you for a question. I think that there is definitely correlation between the quality and the whether we use adapter or the full fine-tuning. But when we talk about catastrophic forgetting, I suppose that empirical studies showcase that it's not connected to the whether you use adapter or the full fine-tuning, so it's more about the data. So it's pretty obvious because why the model forgets everything it has seen before, because your new data doesn't contain anything that was generated before. So these are like parallel stuff, so it's not connected to the LoRA in any way. Does it answer your question?
yeah.
Thank you.
Another one?
Does it work?
Yes, just speaking.
Okay. Thank you for your talk. I wanted to ask you about unit part of your pipeline. So it looks like after all the optimization you introduced, it takes the biggest amount of VRAM memory. And I guess unit is traditionally used for this part of pipeline, but maybe other more lightweight models could be used that have less parameters and take less memory, less VRAM.
Yeah, thank you for a question. Actually, Stable Diffusion is not the new model. There are some approaches which are able to produce more better results, and I suppose that there is a trend to break this generation process into several steps, but I'm pretty sure that all of them are using some sort of mixture of some sort of UNet inside. It's pretty interesting, like whether there exist any other methods. Maybe they are closed source. I personally don't know. So yeah.
Are there any? Okay, another one.
Yeah, I have one more question. So you mentioned you're doing fine-tuning, right? And you had problems with catastrophic forgetting. Do you always exclusively use the Adam optimizer, or have you tried playing around with some other optimizers?
No, as far as I know, Adam is the most like a common optimizer, so it's most popular. So it really doesn't matter at all because like they all are performing optimizations under the hood. But in my opinion, it doesn't matter whether you use Adam or SGD with some additional techniques. So you should get almost the same results in any way.
Yeah. Well, I'm just asking about this because from my experience in like doing things in research, the Atom Optimizer usually does give you fast results, but they don't always have to be optimal. So maybe try something maybe simpler.
Yeah, actually, I do
with which you can play around a bit more, maybe.
Yeah, like I tried to use some SGD to perform this optimization. It also works, and like you mentioned, it produces sometimes even better results, but it takes significantly more time to perform this optimization. So yeah, so you're right.
Yeah, there definitely is a trade-off, but I mean, if you're aiming for like good output, then maybe it's worth the trade-off, maybe.
I don't know. Actually.
No, just a suggestion, yeah.
Okay, thank you.
Another one here. Here.
We've had a question over there.
Okay, so
have you tried multi-GPU optimization? Like, is it limited to a single GPU?
Of course we tried, but you know, like we are doing this stuff in production for different people, so it comes with a price and very large costs on your memory consumption. But these approaches, they work fine in multi-GPU setup.
Yeah, my question was basically about the distributed training. So were there any results that you could share with us if you tried it? So
yeah, I've tried to train LoRa's on my personal photos with this distributed training, and it actually in 2023 it doesn't matter whether it's distributed or not. So you just take some library like PyTorch Lightning or Accelerate, and it does everything under the hood. So it wraps the model with distributed data parallel and other stuff. So yeah, it does.
Thank you.
okay, that'll be it for this presentation. I present you the certificate of being the presenter on DSC. Thank you
very
Alexander.
much.